Okay, last class we talked primarily about the electromagnetic spectrum. We talked about things like gamma rays, X-rays, ultraviolet light, visible light, infrared light, microwaves, the ones in your microwave oven, and radar, spanning the whole spectrum of the electromagnetic spectrum. And we also did some exercises with wavelength, energy, and frequency. There were some tools for remembering wavelength. So on a rainbow, red's the longest, the outside track. That's got the longest wavelength. And violet on the inside is the inside track. It's the shortest path. And they go in color order along with that. There's also visible light switched between ultraviolet light on the violet side, which can hurt you. It can give you sunburn. It can give you cancer, potentially, or increase your risk of cancer. And we've also got infrared light, which is on the red side, will not hurt you, will not give you cancer. So that's low energy. Ultraviolet, UV, is high energy. So violet is high energy, right next to ultraviolet. And red is low energy, it's right next to red or infrared light. So it's like a super fast recap of what we talked about last class. We don't really do calculations with frequency, wavelength, and energy, too much at least. So one of the ways we can model atoms is using the Bohr model. Bohr being spelled this way, named after Niels Bohr. So you may know that neon signs, like this one that we're looking at here that says neon, more frequently you probably see them as open, or it's like some beer brand at a bar or outside of a bar or something, or portrayed in popular media. These signs can light up and they can make a variety of colors. And the way that these work is that typically neon signs are filled with neon. They pump a bunch of electrical energy into the neon sign, and depending on how much energy they put in, a certain color of light comes out. You can actually also do that with other lights or other elements. So a mercury lamp, like the one that we've got here, looks blue. And a hydrogen lamp, so if you put hydrogen instead of neon, it looks this pink color, depending on how much energy you're putting in. So these light, we're going to look at hydrogen specifically, it's the simplest. Light emitted by hydrogen in a hydrogen lamp. So think neon sign, but instead of neon inside, it's hydrogen. If you put hydrogen in there and you give it a bunch of energy, you'll get this emission spectrum. So everywhere that it's black, there's no light emitted, and then we've got these narrow, discrete bands of color along the way. So we've got this reddish color, we've got kind of more a cyan color, we've got maybe a navy blue that's a little hard to see, and something more like indigo or violet or purple. And it's always going to emit those specific wavelengths and only those wavelengths. It doesn't emit anything in between. A white light spectrum, on the other hand, is continuous color. So it's all of the colors from red to violet and every possible shade in between. And this is what you see if like the light comes through a window or off the edge of a mirror at just the right angle. It creates that spread rainbow pattern. That's what's happening. We're separating all the different wavelengths of light out. If you do that for hydrogen, though, again, it's just these narrow, discrete bands. If you move up to helium, which is bigger, it's different bands. Some of them are pretty close, but they're not exact overlaps in terms of where the lines show up on the spectrum. And if you look at iron, which is even bigger than all of these, right now we've got almost continuous sections in some places, but we still have lots of little sharp, discrete bands. So we're just emitting specific colors of light. And so these are emission spectra. Spectra being the plural of spectrum. And this has been known for a long time, relatively speaking, longer than our lifetimes, that only specific wavelengths of light are emitted by these elements when you give them a lot of energy, when you excite them. And Niels Bohr developed a model that helps explain this. So this is the Bohr model of the atom. And this is one that you're probably vaguely familiar with, like the concept of. So on the inside, we've got our nucleus. Our nucleus is where our protons and our neutrons are. The really dense objects in our atoms are just housed in the nucleus. We kind of call it the nucleus. And then the electrons circle on these orbits or tracks. So it's sort of like our planetary model of the solar system, if you don't pay attention to the fact that they're not perfectly spherical orbits. But we've sort of got the sun in the middle, that's our nucleus, and then the planets around it stuck into a fixed track. So that's kind of what we're doing with the Bohr model as well. So we've got our nucleus in the middle, and our electrons can run around on these orbits that are increasing concentric circles larger and larger away from our nucleus. Some features of the Bohr model. These orbits are fixed in place. They have a fixed distance from our nucleus. So if an electron is running around on this n=1 track, it's always going to be the same exact distance from our nucleus versus any other n=1 track from our nucleus. And since it's fixed, another way that we can call that, or another thing we can call that, is quantized, meaning that it's got a set quantity to it. So it's always the same value. It's a set value. That's what quantized means. And these orbits are specified by a quantum number. Quantum is the singular of like a quantity. So we've just got like one value number. So these quantum numbers that are assigned the value n start counting up from 1. It's our most inside track. And we've got shown here up to 4, but it can keep going past 4. So we could go to like 5, 6, 7, 8, however far beyond. And it's also impossible for an electron to exist between orbits. So electrons can only be on the tracks. So they're in n=1, they're in n=2, they're in n=3, they're never in between. And the energy associated with each of these tracks is also fixed. That's what the quantized here was talking about. So the distance that they are away also correlates to energy, so further ones away are higher energy. So our n=1 is our low energy, our n=4, which is the furthest one that we're showing here, is our highest energy. So closer to the nucleus is lower in energy, farther from the nucleus is higher in energy. And the way that the Bohr model explains those emission spectra, where we were looking at the different colored lines, is that since these tracks are fixed and the electrons can only exist on those tracks, in order for them to jump from one track to another, like if we were to jump from n=1 to n=2, the electron would have to absorb some energy to jump to that higher energy track. It would have to absorb a fixed amount of energy since the energy level of n=1 and n=2 are fixed. So every time it jumps from n=1 to n=2, it would be absorbing a certain amount of energy. When it jumps from n=1 to n=2, it doesn't like being at n=2 because it's a higher energy state and it wants to be in its lowest energy state. Like me in the morning when I have to get out of bed to drive an hour to get to work. I don't want to do that. I'd much rather stay in my ground state in my bed and just sleep the day away. But I've got all of your lovely faces to come and look forward to and interact with. So I get out of bed. But at the end of the day, once I'm done being in my n=2 state, I go back home, I lay down in my bed, and I'm back to my ground state. And in order for electrons to do this, to jump from their n=2 to their n=1, or any of these other transitions, to lose energy, they have to emit energy. Because they don't have, they can't dance around and lose their energy that way. They have to emit it another way. And so the energy that they emit is with a photon, which, remember, a photon is our smallest little unit of light. So they emit some energy as a photon, basically one little piece of light, like a little blip of light. So our hydrogen atom, our electron, drops from the n=2 to the n=1, and it releases some energy when it does that. And the light that it emits when it does that is always the same because those tracks are fixed in distance. So it's jumping the same distance every single time. So it's always going to emit the same energy level of light. And we learned last class that color of light, of visible light, is related to the energy. So if it's violet, it's a high energy photon, it's high energy light. If it's on the red light end of the spectrum, it's lower energy. And because energy on our spectrum relates to color, the transitions between these levels also correlates to color. So for example, this might be what the correlation is for our hydrogen spectrum. So our lowest energy transition is this red line on our emission spectrum, and that would correlate to our lowest energy transition, which might be our n equals 2 to n equals 1. So an electron gets excited up to n equals 2. That's because of all the energy that's getting pumped into our hydrogen gas. So it gets excited up to n equals 2, and then at some point, some period of time, it decides, I want to go back, and it releases a photon of light. And because this is our smallest transition that we're looking at here, we would say that that probably correlates to our red light. It could also, though, get excited up to n equals 3 if it absorbs more energy, because it's a further distance. We can see that, right? So it's n equals 3 to n equals 1. That's a longer distance, so it would have to absorb more energy to get there. And then when it relaxes, it's also a further distance from n equals 3 to n equals 1 than it is from 2 to 1. So because it's jumping down a longer distance, it's releasing more energy, and that's light that's closer to the violet side of the spectrum. And the same thing is true for this n equals 4 to n equals 1 transition that might correlate to this one that you can't really see on the slide in the class. But there is a color there, I promise. Questions so far? So the longer distance that it jumps, the higher the energy that's going to be released, the color of light. They don't always have to jump back down to the n equals 1. For example, like if it's at n equals 3, it could jump to n equals 2 first and then jump to n equals 1 second. So then it would release 2 separate bursts of light, 2 little photons, to get rid of its extra energy. So our 2 to 1 is our lowest energy transition that we're looking at here. And so that's our lowest energy light. Longest wavelength, which means that it's the lowest energy. And our bluish light, purplish light, is a shorter wavelength, and so that's higher energy. And perhaps fortunately, maybe unfortunately, we don't do any calculations with this. It's just we would compare, the n equals 2 to n equals 1 transition. How does the energy from that transition jumping from 2 to 1 compare to maybe 3 to 1 or 3 to 2? Another thing that's important about these rings is that 1, that's our closest ring, to 2 is a set distance. And you notice, hopefully on this slide it comes across, 2 to 3 is a smaller distance than 2 to 1. So as we move further out, the rings get closer together, which is especially noticeable with our transition between 4 and 3. And that's also true if you go past n equals 4, which can happen. Just for the sake of room, I didn't include it here. So our 1 to 2 is our biggest jump, 2 to 3 is smaller, 3 to 4 is even smaller, and so on and so forth. So one of the great things about the Bohr model is that it predicted the lines of the hydrogen emission spectrum. So not only does it explain it, but you can also put numbers to it and calculate okay, well, if I had this transition, then it would be this certain amount of energy, which we aren't doing. And so they were able to show that this model works, and it also predicts other things. It's not just an explanation. However, the Bohr model, albeit though is a great success, failed to predict the emission spectra of other elements. Anything that had more than one electron, it could not predict. So it could predict for hydrogen, it could predict for helium, if it was a helium plus ion, so it only had one electron, and other larger things that only had one electron. It could predict those emission spectra, but it didn't work for anything that had more than one electron. So hopefully you haven't grown too attached to the Bohr model, because we're saying goodbye, Bohr model. I know it's been a fast relationship, but such is the way of things. So our Bohr model was replaced with a more sophisticated model called the very scary quantum mechanical model. You may have heard about quantum mechanics. You may also remember I said that quantum is like the singular quantity. So like you may not be familiar with the word data. Data is a plural, and one point of data is datum. It's the same sort of language stuff that's going on here. So a quantum is like the smallest singular quantity. So when we're talking about a quantum mechanical model, we're talking about the very smallest things in the world. So we're talking about like singular pieces of light, really, really small, tiny things. That's generally what we're talking about with quantum mechanical. And then the mechanical part is like, how does it work? So quantum mechanical model, we're just trying to explain how the smallest things behave. And it's not intuitive. Did you hear me? It's not intuitive. It will probably not make sense. That's okay. But we can still memorize some of the terms, even if it doesn't like map well onto anything that we understand. It's weird because it's really, really small. If you've seen Quantumania, the Marvel movie, things get really weird when they get really small. Things get really weird when we get really small when we're talking about atoms and electrons and energy. So we are reusing some of our Bohr model ideas. We're not completely throwing it out, but we are updating some things. So the quantum mechanical model is revolutionary because electrons don't actually behave like particles flying through space. So they don't actually just run around on nice little orbits. Instead, they, in my mind, just randomly teleport, which is cool. I don't know if that's entirely accurate, but that's what my brain retains, is that the electrons just randomly teleport. They can be anywhere at any given moment, which is really fun because it's super unpredictable. Our Bohr orbits are also going to be replaced with quantum mechanical orbitals. So our orbits were those tracks that we had around our nucleus, right, where our energy levels were. We're replacing those with orbitals. One of the trends holds, though. So if we go to a bigger orbit, we're increasing in energy. If we go to a bigger orbital, we're also increasing in energy. So some of the ideas still track. And in many cases, you can still think of orbitals as being related to orbits. So the reason that I say that electrons just kind of teleport around, our orbitals are probability maps. And these have specific shapes. And these show the statistical distribution of where an electron is likely to be found. So we'll have some shape that we'll define, and we'll say 90% of the time maybe the electron is found in this area, whatever the shape is. 10% of the time it could be anywhere else outside of that shape, and we're not sure where it would be. We also don't know at a given point in time that the electron is actually in that area, but our best models show that it is. This is sort of like, these probability maps are sort of like if you've got a best friend, hopefully you do, and you kind of have a general feel for their schedule. If somebody asked you at any given time, hey, what's your best friend doing right now? Where are they? You could say, well, I know that it's this time of this day, they're probably in class, or they're probably working their shift at whatever store they work at. And most of the time you're probably right, because you know their schedule really well. So you've got a high probability, but they might have a doctor's appointment they didn't tell you about. They might have some family thing that came up. They might have just overslept and they're still in bed. So probability maps are sort of like that. We know our besties are electrons. We know where they're likely to be found. They're not always there. And now we've got some fun quotes from famous physicists about quantum mechanics. So from Niels Bohr, the Bohr model guy, anyone who is not shocked by quantum mechanics has not understood it. From Erwin Schrödinger, the guy with the cats, I don't like it and I am sorry I ever had anything to do with it. From Richard Feynman, one of the most famous physicists, I think I can safely say that nobody understands quantum theory. Okay, so we're in good company if we're confused. We are joining the rest of the people who know about quantum mechanics in that we don't know really what's going on. So that's fun. Fortunately for us, perhaps, the math and calculations that are behind quantum mechanics are beyond the scope of this course. So we are just learning the concepts. If you want to learn the math and calculations, you're welcome to consult Wikipedia. It's like looking at a foreign language because there's so many new terms and there's all these new words, and you also have to know calculus and sometimes some very complicated calculus. So we're just going to focus on the terms. We'll learn some shapes, we'll learn some numbers, we'll learn some letters, and we'll call it a day. But it's still powerful, it still informs some of our ideas about other things, and you'll use it in the future if you take more chemistry. Okay, so transitioning from our orbits to our orbitals. Remember that our orbit is a circular path. Obviously, I'm not great at drawing circles because few people are. So we've got our nucleus and our orbitals are just a nice circular path around that. Our orbitals are probability maps. Again, these are shapes. We'll learn some shapes. Not like square, circle, rectangle, triangle, not those sorts of shapes. But we'll learn some shapes. And these show the relative likelihood that our electron is in that shape. So our electrons are most of the time going to be in that shape. But these are relatively unpredictable compared to our nice, neat electrons spinning on a circular track. Our orbitals are specified with a number and a letter. Our number is called our principal quantum number. Principal quantum number because it's our first quantum number, it's our big quantum number, instead of just quantum number. We're reusing the same symbol for it. It's still going to be the lowercase letter n. For our orbits, that specified which track we're on. For our principal quantum number, this specifies still sort of like the size of the shape that we're talking about. So the lower numbers are still lower energy, the higher numbers are still higher energy. So you can sort of still think of it like the big tracks, high energy. In case of our principal quantum number, it's going to be bigger shapes. And they start from n equals 1, going to n equals 3, and so on. A higher number means higher energy. So the letter then that goes along with it indicates the subshell, and this is the shape. Really, it's shape families, families of shapes, sets of shapes. And our letters are S, P, D, and F. So for example, we can have 1s, we could have 4d, we could have 6f. There are some of these pairings that are not allowed, and we'll learn about which ones of those are not allowed. There's some rules about when they come up. So we need to remember that our principal quantum number is n, and that is a number. It starts from 1, and it counts up, 1, 2, 3, 4, etc. And then our subshell is the letter, and the subshell is just the shape. So a letter equals a certain type of shape. And our options are S, P, D, and F. So our 1s comes first. So 1s is our shape, our lowest energy shape. It's lowest energy for a couple of reasons. One of them is that our n equals 1. Our principal quantum number is 1. That's the lowest value that we can have. And S, as it turns out, is also our lowest energy shape. Our orbitals, unlike our orbits, are also in 3 dimensions. So what we're looking at is a plot with 3 axes. So our x would be the one that's coming out of the board. Our y would be the one that's in the plane of the board, but like left to right. And then our z is the up and down. And sometimes you'll see these labeled differently, but this is like a typical 3-dimensional plot. So this S orbital that we're looking at, on the screen it looks flat, but in reality it's more like a sphere. So that's really nice and convenient. S orbitals are spherical, so S for sphere. Isn't that fun? Do we have questions or confusions yet / so far? Again, if you're confused, that's normal. It's sort of just like memorizing a weird game, especially for quantum mechanics. It's really like memorizing a weird game. So if S is for sphere, does anyone want to guess what P stands for? It would be so nice if it stood for prism. We'll get to it. I'm getting a little bit excited. Getting a little ahead of myself. Okay, so our 1s, that's our lowest energy. We're always going to start from 1s. If we've got a hydrogen atom and it's just chilling at room temperature, it hasn't been zapped with a bunch of electricity, then it's in what we call the ground state. Like being in bed, or even if you're so tired that you can't get into your bed, literally on the ground state is our lowest energy state. Typically, unless you're disturbed, unless you've got something else to do, ground state is where we're going to find especially our elements. It's probably also true for us. If you get energy that's absorbed, if you're an electron, if there's some energy that's absorbed, that can cause the electron to jump to a higher energy orbital. And this is called an excited state. Excited states are unstable. Meaning that they're temporary. So like with our orbits, where we had the tracks, right, we could inject some energy, give our electron some energy, and it jumps out to the n equals 2 or the n equals 3 or the n equals 4. And then after some period of time, beyond the scope of this class, the electron says, I'm going back to the ground state, and whoop, drops back down to the ground state. And when it does that, it releases that little photon, that color of light that we were seeing on our colored lines, our emission spectrum.
I have a question. That
yes.
Photon light, would that be like radiation as well?
It is radiation, yeah. Yeah, it would count as radiation. So it radiates, it releases some light. All atoms, the atom is going to have one ground state. There's one lowest energy form where you put all the electrons into the lowest energy state, and there are many excited states. Because even just for our hydrogen, we could jump our electron up to the n equals 2. That would be one excited state. N equals 3 would be a different excited state. N equals 4, a different excited state. And there's other options. And for everything that's got more electrons, there's more ways that we can shuffle our electrons around so that they're in weird states. We will generally focus on ground states, which is great news for us because that limits our options. So we're going to focus on what's the lowest energy configuration available, and we'll learn to read those. All right. Getting back to our numbers and letters, our n equals 1 principal quantum number, or principal shell, contains one subshell. It contains one shape, and that's S. So we just have one S. Our n equals 2 principal shell, so we jumped up to a higher energy level. We've got two subshells. We've got S, we also have P. And our 2s orbital is higher in energy and a little bit larger than our 1s orbital. So this tracks with the Bohr model. If our 1s is this little sphere, our 2s is a bigger sphere, and our 3s is an even bigger sphere. Any guesses on what our 4s would look like?
Even bigger.
It would be just a bigger sphere than our 3s. Just slightly larger spherical shape. And S, of course, stands for sphere, and so naturally P stands for whatever this is, dumbbell, usually. So P for dumbbell.
Peanut.
Or peanut. That's great. P for peanut. Assuming that it's a very normal and slightly elongated peanut. So our 2p subshell, this is our first occurrence of the P shape, the P subshell, contains 3 orbitals. So we had one sphere for our S, and we've got 3 dumbbell shapes or peanut shapes for our 2p subshell. So 3 orbitals, 3 shapes. The orbitals are specific shapes within the family of shapes. So P is just our peanut shape or our dumbbell shape. You don't need to know the sublabels, but I think they're interesting. So we've got PZ, PX, and PY, and these are just the dumbbell aligned along that axis. So PZ, the long way of the dumbbell, is going through or tracking along with the Z axis. For PX, it's on the X axis. For PY, it's on the Y axis. So these are just 3 different orientations of the same shape, and they don't overlap with each other. In reality, this is not exactly quite what the P shapes look like, I think. But this is usually how they're shown, is these dumbbell shapes. The dumbbell part is correct. I think they're just actually a little bit more squat. They're a little bit more Toad from the Mario universe. They're a little bit more Toad head shaped rather than being these nice long dumbbells. Okay, so the number of subshells in a given principal shell, for our lower numbers at least, is equal to n. So for our n equals 1 shell, that's our smallest, if we're thinking about orbits, that's our lowest energy n value. We've got just the one subshell, and that's our S, or a sphere. When we get up to n equals 2, when we jump up to a slightly higher energy level, we've got S, but we also have P. That was our peanut or our dumbbell shape. When we jump up to our n equals 3, we've got 3 subshells. We've got S, P, and D. And then it's in shell 4, n equals 4, that we unlock the F subshell, which we're not going to look at because it's scary. I don't remember what they look like. I know that they are awful. I didn't like them. I still don't like them. So I don't show them to you. I don't want to scare you away. Okay, so this, by the way, would be a good thing to have memorized. There are other ways that we can come up with the order, like when the subshells come up. There's a game that we can play with the periodic table that we can use for that. Okay, so our n equals 3 principal shell. We still have our S, our spherical shape. We still have P, our dumbbell shape or our peanut shape. The 3s and the 3p orbitals are going to be the same shapes. So 3s is still a sphere. 3p is still dumbbells. It's just bigger dumbbells. So our 3p dumbbells, or peanuts, are bigger than the 2p dumbbells, or peanuts. And they contain, right, we have the 3 different dumbbell shapes. Our D subshell, this is the first time that D is coming up, and D's got 5 orbitals. Are we ready to see our D orbitals? These ones are actually kind of fun, I think. Okay, so here's our D orbitals. And so D, generally, we could think of as standing for double dumbbell. So notice that we've got 2 dumbbells for 4 of these. And then we've got this weird one that's got a dumbbell along the z-axis, and then it's got a torus, or a donut, that runs around it. You don't need to have the D shapes memorized. I just show them to you because it's like helpful to have something to think about. You also don't need to know the labels. The labels, though, if we look at this XY, DXY, our double dumbbells are between the X and the Y axes. So they're kind of like 4 directions and then turn a little bit. And then our x squared minus y squared is along the x and y. Our dz squared is along the z. And we have a donut for some reason. So those are our D subshells. And again, we don't look at the F subshells because they're really weird. They're like triple dumbbells, quadruple dumbbells. Scary stuff. Okay, before we get into electron configurations and where our electrons go, do we have any questions about our principal quantum number n, or our shapes, or our orbitals, our subshells, s, p, d, f, or our individual spheres, dumbbells, double dumbbells? Cool. Again, these shapes describe, like for this dxz, an electron that's in this particular subshell, this particular orbital. Our electron is likely to be found. It's most of the time going to be found in this sort of a weird shape. So if you like took a picture, every time that the electron moved, it would plot out to something that looks sort of like this. For our spherical one, for our 1s, our smallest orbital, if you took a picture, lots of little pictures of where the electron is, and you made it into an overall shape, it would look sort of like that spherical shape. Okay, so the way that we talk about where our electrons are is with an electron configuration. This tells us where the electrons are. And we will be focusing on the ground state, which is the easiest. So for a ground state hydrogen atom, so hydrogen, our symbol, we've got our orbital, which is 1s. So 1's our lowest principal quantum number. S is our first shape. In n equals 1, we just have 1. We just have s, so 1s. And then this number up in the top right corner is the number of electrons that we have. How many electrons does hydrogen have?
1.
It has 1. So if we look at it on the periodic table, if you look in the top right corner, that 1 is the number of protons that it has. It also has the same number of electrons, so it has 1. So we only have to place 1 electron for hydrogen, and so it goes into the lowest energy orbital, which is our 1s. So it's 1s1. We can also do an orbital diagram. An orbital diagram is an electron configuration, but with a little bit more information. So this is kind of like a visual electron configuration. Usually we're going to do an electron configuration, and then after that we'll do an orbital diagram. But again, it's just like a visual version of our electron configuration. So we're going to have boxes. This box is representing our 1s orbital, so our smallest sphere. In our smallest sphere, we've got one electron, and we've drawn it in as an up arrow. Our options are up arrow or down arrow. So electrons are up or down arrows. In this case, we've drawn it in as an up arrow. Since we just have one, we could have also drawn it in as a down arrow. I think that would be equally correct. I just always draw up as the default. And again, we just have the one electron, so we just draw the one up arrow. In our orbital diagrams, the direction of the arrow represents electron spin. Electron spin is just a property of the electrons. And you're going to love this. The names for the spin are up spin and down spin. So the direction that they're pointing, up or down, is the spin, up spin or down spin. And I'm not joking, that's like the actual, that's how they call them, up spin, down spin. And we're learning our first of two, I think it's just two, principles or rules that go along with this. So we've got the Pauli exclusion principle, our orbitals, so our little boxes like our 1s box, those boxes can hold no more than 2 electrons, so we're capped at 2, and they have to have opposite spins. So maximum of 2 electrons per box, and the boxes there are representing our individual shapes. So for S, we just had the one spherical shape. For P, we're going to have 3 boxes because we've got 3 different dumbbell shapes. You can only get 2 electrons into each of the 3 shapes, each of the 3 dumbbells, and they have to have opposite spins. So maximum of 2 electrons per box. Spins must be opposite. So some things that are allowed. I typically draw my boxes in as just a line. So for helium, we've got 2 electrons because our atomic number, that number in the top right corner, is 2. So we can place 2 electrons. 1s is still our lowest energy. So the correct way to put it in, I usually use one-sided arrows. We would put in up and then down. So we've got 2 electrons, no more than 2 electrons, and they've got opposite spins. One's pointing up, or one's spinning up, the other one's spinning down. So that passes. There's some ways that we could screw this up. So I'll show us some ways that we could screw this up. So again, with our 1s, it would be wrong to put 2 arrows up. 2 arrows up wouldn't have opposing spin. They would have matched spin, and that's not allowed. It's forbidden. It would be equally as wrong, but in a slightly different way, if we drew them both with down spin. Functionally, I don't think it makes a difference, but this would also be wrong, because spins must be opposite. And then a third way that we could make this wrong is if we had lithium with 3 electrons and we had like up, down, up. That's too many electrons. We can't fit 3 electrons into one box. So that's too many electrons. Okay, so those are a couple of ways that we can be wrong. maximum 2 electrons per box. They have to be opposite. So we can write electron configurations and orbital diagrams for helium and lithium. We already did helium. So helium has 2 electrons. Our lowest energy orbital, our lowest energy letter, number, and letter pairing is 1. 1's our lowest energy number. And S is our lowest energy letter. So we've got 2 electrons to place. We can put one up and then the other down. We've placed our 2 electrons. So they've all been placed. We're done. That's our ground state for helium. For lithium, we have 3 electrons because our atomic number, that number in the top or in the top right corner, is 3. Our lowest energy is 1s. We can place 2 electrons into 1s. So we'll have up and down. So after we place our 2 electrons into 1s, we still have 1 electron. Where do we put our electron? We're going to need another box. So what box do we think might come after 1s? 2s. If you said 2s, you are correct. So 2s comes next because 2 is a bigger number, and s is still our lowest energy shape. And we can put that last electron in with upspin. Downspin, I think, would also be correct, but I put it in as upspin. So now we've got all 3 electrons placed. So that would be a complete orbital diagram. So if we've got, this is fun, you're going to love this. If we've got multi-electron atoms, like with helium, lithium, and everything else on the periodic table, the subshells do not have the same energy because of electron-electron interactions. So the electrons that are in the boxes, right, in the different shapes, like in our peanut shapes, our double dumbbell shapes, plus the dumbbell with the donut, those electrons can interact with each other. They can kind of like sync up or harmonize in terms of like their frequency and the way that they're jumping around, moving around. And that can change the energy level of those electrons. So if they're all synced up, that actually lowers the energy of the electrons. So if we plot all of our different number and letter pairs, so our S, P, and D, just looking at our S, P, and D orbitals or shapes, and we've got energy on our y-axis, they're offset just so you can see that they show up differently. If we look at just our S, right, 1s, 2s, 3s, 4s, 5s, we're just counting up the number, which makes sense. 2p, 3p, 4p, and again we've got 3 boxes because we've got the 3 dumbbell shapes or the 3 peanut shapes. So those also go in the order we would expect. For D, 3D, 4D, we're counting up still. We've got 5 boxes because we had the 5 different shapes. What's not necessarily intuitive is we go from 1s to 2s to 2p. That's normal. Then we go to 3s, 3p, and you would expect that we would then go to 3d. That is not the case. We instead go to 4s. And then after 4s, we go to 3d. Instead of to 4p, we go to 3d. Then we go to 4p. Then we go to 5s. Then we go to 4d. And it gets more complicated the more electrons that you have. So the energy levels generally, like within a letter, increase as the number goes up. That's true. However, which one comes next is not necessarily intuitive because we would expect it to go in order, right? We would expect 1s, then 2s, 2p, then 3s, 3p, 3d, because that's where our d orbitals show up for the first time. And it's not that way, unfortunately. However, we will learn a trick for coming up with those orders. There's a couple of tricks. The periodic table is the best one. So we'll come up with some of those tricks. For now, let's stick to things that are smaller. We don't have to worry about the order of things, or I'll just give you the order. We can do an electron configuration. That's where we had the number, the letter, and then the little number in the top right corner for how many electrons are in there. And we can also do orbital diagram, and we're going to do this for carbon. Carbon has the symbol C. How many electrons does carbon have? Carbon has 6 because its atomic number is 6. So we have 6 electrons. We know that 1s is our first. So we're going to start 1s. How many electrons can we fit into our 1s? We can fit 2, because we've got the one spherical shape, 2 electrons. So 2. So we've used 2 electrons, meaning that we've got 4 electrons left after that. After 1s comes what we would expect, 2s. We can also fit 2 electrons into 2s. So we'll place 2 electrons. And we've got 2 electrons left. Those 2 electrons can go into our next number and letter combination, n equals 2, and our letter is p. We can put both of those electrons in there. So 2p2, placing our last 2 electrons. So we're done. That's our electron configuration. Now that we've got our electron configuration, we can draw out our diagram. So we can draw out with the up and the down arrows. What does it look like? So we're going to use these 1s, 2s, and 2p labels for our boxes. Again, I'm just drawing a line because I'm lazy. So we've got 1s first. We've got up and down. We've maxed out. We've got our 2 electrons. They've got opposite spins, up and down. Next comes our 2s, because that's what we've got next in our electron configuration. We've got 2 electrons, so it's full. We're going to have up and down. And then we get to 2p. And for 2p, each of our boxes represents one of our shapes. And in the p, we had the 3 dumbbell shapes, so we're going to have 3 boxes. And when we place the electrons in, we've got 2 electrons to place. It doesn't really matter which of these that you put them into, because we don't have them sub-labeled. You could label them px, py, pz, the labels of the shapes that we saw. We're not going to do that. So we're just going to treat them all equally. So I just start from left to right. And we have to put them in up and up. So this is our second rule. It's Hund's rule. So when we're filling orbitals of equal energy, like 2p or 3d or 4d or any of our f orbitals, where we've got multiple shapes, our double dumbbells, our single dumbbells, we need to fill the electrons in singly first with parallel spins. So we'll do up, up. If we had another one, that one would also be up. And then after they're all up, then we can start adding them in with downspin. It's our second fun orbital diagram rule. Questions so far? Okay. And that reminds me. our S has how many shapes? For the letter S, how many different shapes do we have? What's our shape for S? It's a sphere. So for S, we've got one sphere. For P, we had how many shapes? It's the peanut shaped, right? How many of those peanuts did we have? 3. For D, we had how many shapes? We had 5. And those were the basically double dumbbell. We didn't look at F, but if we had to guess, F comes next. How many shapes do you think F might have? If S has 1, P has 3, D has 5, how many does F have?
7.
It has 7. Freaks. Because they look really weird, maybe. They look crazy. They look really, truly crazy. So 1, 3, 5, 7, as you'd expect. Another, fortunately for us, we don't learn, there's numbers that go along with the different shapes, and we don't learn those either. But you will learn those if you take more chemistry. Okay, so we've got an analogy, the quantum hotel. So if we think of our electrons as residents, people that are coming to stay in our hotel. This is not my chemistry line, by the way, because I'm Mr. K. So this is Mrs. K's chemistry line, not my wife, my mom. This is a weird hotel. It's this like upside down pyramid shaped hotel. Because it's the quantum world and things are weird. So our first floor, we've got one room, and it's just the S room. Our second floor, we've got 2 rooms. It's our S and P. The third floor has S, P, and D. And you add up to 4 when you get to 4. 5 also has 4 rooms, and so on and so forth. And these floors are basically like our principal shells. Or if we wanted to think about them like our orbits from the Bohr model. They're increasing in energy. Any of our S rooms is going to have 1 bed. Our P room is going to have 3 beds. Our D room has 5 beds. The beds are the orbitals, the different shapes. Our subshell is the different letter designations, S, P, D, or F. And these are not big beds, and so you can only have 2 people. The people are the electrons. You can have 2 people per bed, and they have to have opposite spins because they're weird about it. So if you think about if you and 3 of your besties, so there's 4 of you, or maybe let's say you and 2 of your besties, if you've got 2 besties, right? 3 people, and you're going to stay at a hotel, and the hotel room has 3 beds. What's the most logical way to arrange yourself into those 3 beds? Every person gets a bed. If there's 3 people and there's 3 beds, chances are you're each getting your own bed, and you're probably all sleeping with your head to the wall because you're not a freak. Because that's how people normally sleep. If you sleep with your head not against the wall, you're not a freak, it's just weird. So you're going to have everyone sleeping in their own individual bed. Let's draw out the beds. Right, so you're going to sleep 1 person in each of the bed. This is with 3 people and 3 beds. If we have 4 people, 4th person, you might Rochambeau, or maybe somebody's extra besties with the 4th person. But now we have to put somebody in one of these beds, and again, because we're weird about it, right? They sleep head to foot, because it's like, elementary school summer camp or something. And then if you had a 5th person, you're not going to throw 3 people into one bed, because they're not going to fit. You're going to throw the 5th person into the next bed, and you're going to throw the 6th and final person into the last bed. And if somebody tried to say to you, hey, we've got 3 twin beds and 7 people, do you think you can fit? You'd say, no, put them in a different room, right? So that's maybe one of the ways that this chemistry line can be helpful. And we will stop there and pick up next class so that we can do our ions quiz.